guys, in this video we're gonna continue the study of Riemann integral. Remember in last video we have already studied the concept, the definition of lower sum and upper sum, and we have seen some pretty good properties and lemmas, right? So and in this video we're gonna officially introduce what the Riemann integrability is, and another criteria for the integrability, and some interesting theorems. Well, probably only one theorem in this video, but a lot more in the next videos. So, well, first of all, remember so let's first recall the upper and the lower sum. The upper and lower sums are actually they're related to the partition you choose, right? The lower sum is taking the sum of the infimum value of each interval times the length of that interval, and the upper sum is correspondingly defined. And we will take a further step of the upper and lower sum, which is the upper and lower integral. So remember, in the previous video, the upper sum and lower sum, as I said, they are related to the partition you choose, and the upper and lower integral kind of like get rid of those partition. So the upper sum will be the infimum of all the partition of in that interval AB, and the lower sum will be the supremum of the lower sum in that interval. And well, if you remember, I said in last video that ideally we want to approximate an integral such that we want to approximate the integral by the lower sum and upper sum such that the gap between lower sum and the upper sum will be so close that they are almost the same, right? And actually, we define the upper and lower intersum. This is the reason why we define upper and lower integral, right? Because we are taking the infimum and the supremum of our upper and lower sums, kind of like taking the limit of, kind of like we are looking for a finer and finer partition, and finally these two upper and lower integrals are so close that they're almost the same. And this is actually how we define the Riemann integrability, or how we define the integrable function. But here we have to pay attention is that the function here about Riemann integrability that we are going to talk about are those like bounded functions. So a bounded function f defined on an interval AB, and the interval is given as a compact interval, is Riemann integrable if the upper integral equals to its lower integral, and the value of the integral of the function will be equal to its upper and lower integral, right? And another lemma I forgot to say about the upper and lower integral is that, well, actually we have seen the similar consequence in the upper and lower sum, right? So the lemma says for any bounded function f on AB, we have the upper integral always larger or equal to the lower integral. This is quite straightforward and obvious, right? Because, well, if you are taking the same partition, then the way you define upper and lower sum is you are looking for the supremum and infimum in that interval, right? And in that interval, right? And the supremum will be always larger or equal to the lower the infimum, right? In that interval, in each interval, It's always the case. So we're not gonna prove this lemma. It's quite obvious. And I said in the beginning of this video that we're also gonna introduce the criteria for integrability. So that is to say, besides the definition of how we define a Riemann integrable function, we will also have another criteria for integrability. So this it is the same way that we define uniform convergence sequence, right? Because we have the definition for uniform convergence, and we also have a criteria for uniform convergence. And this is quite convenient because you don't have to stick to its raw definition. You have other choice to prove the integrability, right? Okay, so the theorem says a bounded function f is integrable on AB if and only if there exists for any epsilon larger than 0, there exists a partition p epsilon in AB such that the upper sum of f with respect to p epsilon minus the lower sum of f with respect to p epsilon will be smaller than epsilon. I think this is intuitively quite easy to understand, because when we define the integrability, we define it as to be like the upper integral must be equal to the lower integral, and the upper integral and lower integral are essentially taking the limit, right? Taking the limit of your upper sum and the lower sum, right? And upper sum and lower sum are simply upper sum and lower sum are related to the way you partition the integral. The upper integral and lower integral are taking the infimum and supremum of all the partition that you can get in a given integral, given interval AB, right? And if you when you are given epsilon, a small gap, epsilon larger than 0, if you can find some partition such that under this partition the difference between the upper sum and the lower sum is very small, and actually if you are taking epsilon smaller and smaller, very close, extremely close to 0, then if you can still find some p epsilon, some such partition such that this inequality holds, then it's almost the same that UF p epsilon is almost approximately equal to the lower sum of f with respect to p epsilon, right? So I think this is the intuitive way to understand this criteria, and we're gonna prove it. Okay, so it's still a sufficient and necessary theorem. So, well, first of all, it's if we are given already the condition that if we are given that for any epsilon there exists a partition such that this inequality holds, then it's quite easy to prove f is integrable, right? Because, well, simply by its definition. So suppose we already have, suppose we're given some epsilon larger than 0 and epsilon is arbitrarily chosen, and assume then we have p epsilon. Then what we get is that by the condition we have uf minus UF minus AF, the difference of the upper and the lower integral will be smaller or equal to UFP epsilon minus FP epsilon, right? Which is smaller than epsilon, because, well, UF is taking the infimum of UFP, so it will be always smaller or equal to UFP no matter what epsilon you're choosing. And similarly, FP is always larger than FP no matter what P epsilon you're choosing, right? So this inequality holds. And since we are habitually choosing epsilon, when we are taking the limit of epsilon, when epsilon goes to 0, then the difference of UF and LF goes to 0, which is equivalent to saying that UF is actually equal to LF. Right? It's quite straightforward. Okay. On the other hand, if we are given that this function is already integrable on AB, how are we gonna prove that UFP epsilon is minus LFP epsilon is smaller than epsilon? It's again a inequality, and the way we prove it, the first hint is that you use triangle inequality, and this is a very common way to prove such like integral like this. And to use triangle inequality, you are actually choosing some looking for some help, right? Because otherwise you have only UFP epsilon and LFP epsilon. They look a bit like unrelated. You are looking for some help to give you some more information about U and UFP epsilon and LFP epsilon. And since we wanna show, that it's integrable, since we wanna show that it's it's already integrable, and we want to show there exists a partition P epsilon, then it's basically saying that we are going to find such epsilon. So the task is to find P epsilon, right? So P epsilon is not coming from nowhere. It's actually, well, since we have, remember F is not integrable, and we have UF by the definition is equal to infimum of UFP for OP. Then for some epsilon, we will have a partition P1 such that UFP1 will be smaller than UF plus epsilon over 2. Or you can just say epsilon. It doesn't matter. I choose epsilon over 2 because at the end of the proof, it will come together to be a nice epsilon. But actually, it's reasonable here you choose only epsilon. And similarly, by the way, this inequality comes from the definition of infimum. If you don't remember it, just go to click the video for infimum and supermum. And similarly, we will have P2 such that air FP2 will be larger than air F minus epsilon. Alright. Okay. These two epsilon are the same because for some epsilon, we first kind of like fix the epsilon, and then we will have then now it's time to choose P epsilon. P epsilon is neither P1 nor P2. P epsilon is chosen to satisfy both P1 and P2. So P epsilon is the refinement kind of like the refinement of P1 and P2. Right, it's find the refinement of P1 and P2, and then what's next? We will have UF P epsilon minus LF P epsilon smaller or equal to these two inequality now holds, both holds. So smaller or equal to UF P1 minus LFP1, right? LFP2, sorry. And here I also use some lemmas in the last video, because P epsilon is a refinement of P1 and P2, so UFP epsilon will be smaller than UFP1, right? And what we also have is that then UFP1 UFP1 minus LFP2 is then equal to UFP1 minus UF plus LF. This part equals to 0, right? Because F is integrable, and then minus LFP2. This is the thing that we are seeking to help us. I said before, only UFP epsilon and LFP epsilon might be a little difficult for us to find its relation. So relationships. So we are trying to get some help from other like values. Okay, so then we have UFP1 minus UF and LF minus LFP2. So then this is smaller than epsilon minus epsilon, which is 2 epsilon. And we're done. Well, so the reason why I originally said there's gonna be epsilon over 2 is that I wanna to make sure this part at the end of the proof I wanna get only epsilon, so this part will be half epsilon plus half epsilon, but it's totally fine if you finally get 2 epsilon, because epsilon can be extremely small, right? It doesn't matter if it's 2 epsilon or 4 epsilon, 100 epsilon or epsilon over 12, it doesn't matter, right? Okay, so next, it's a very nice theorem. It connects the continuity and integrability of a function. So now f is continuous on the interval AB, and then the consequence is that it is integrable on AB. So continuity can take us to the integrability, but it has to be sit on the compact interval AB. Okay, so given a continuous function on AB, what do you get from this condition? Well, first of all, f is not only continuous but also uniformly continuous, which is a more strict, like continuous in a more stricter way. In a stricter way. So f is uniformly continuous. Which is, given epsilon larger than 0, there will exist a delta, a positive delta, such that if if 2 points are close, so close that the distance between them is smaller than delta, we will have fx minus fy, taking the absolute value of it, will be smaller than epsilon over b minus a, over the epsilon over fx minus fy will be smaller than epsilon over the length of the whole interval. Right. Okay. So the point is, how are we gonna choose? Sorry, I forgot to mention, the way we prove this theorem is by the with the aid of the criteria for integrability. And to use the criteria, the thing is we have to find a partition P epsilon such that the inequality holds UF P epsilon minus LF P epsilon is smaller than epsilon, right? So actually we already have an epsilon. And we have also a delta, and then we are going to choose some partition, right? So the way we choose the partition is that we are taking every subinterval of P epsilon to be smaller than delta. That is to say, delta x equals delta xk which is equal to xk minus 1 is always smaller than delta. This is the way we partition the interval AB. But each subinterval might not necessarily be equal. The length of each subinterval might not necessarily be equal. Okay, so let's look at a graph. Say this is our AB might be like far away, and this is our small subinterval xk minus 1 and xk. What we know is that f is continuous on a compact interval AB. What else do we know? By extrema values theorem, we know that in this interval, the function takes its maximum and minimum, right? So we must have some, say in a particular subinterval xk, we must have some zk in xk minus 1 to xk, and we have mk, the maximum value of the function in this interval is equal to fzk, and there exists yk in this small interval such that the minimum mk is equal to fyk. So remember, originally the way we defined mk, capital MK and mk is that we take the infimum, so we take the infimum and the supremum, but in every subinterval, since f is continuous in every compact subinterval, we have that we still take the supremum and the infimum, but in fact we can touch that limit. We have that zk and yk such that fzk and fyk touch the supremum and touch the maximum and minimum of that function. So then, remember, this might be zk, and here this might be yk, right? This is minimum, and it's obvious that zk minus yk, the length of these two numbers will be smaller than delta, right? Because they are obviously smaller than xk minus 1, right? And so then fzk minus fyk will be smaller than epsilon over b minus a. This is because the uniform continuity of the function, right? and this is equal to mk minus smaller than mk, right? So we have capital mk minus mk is smaller than, we have this inequality, smaller than epsilon over b minus a. And finally, when we take uf p epsilon minus lf p epsilon, we will have, well, by definition, we will have the sum from 1 to n of mk minus nk times delta xk, right? Because this is the way we define the upper and the lower sum. We simply taking the summand together, because otherwise you can write it into the sum of capital MK times delta xk minus the sum of small mk times delta xk, which is, well, basically equal to mk minus capital MK minus small mk times delta xk, right? And this will be smaller than, well, since delta xk is always smaller than delta, and mk minus capital MK minus mk is smaller than delta over b, epsilon over b minus a. And sorry, here we are not using delta xk smaller than delta because, or use it, it's doesn't matter. If we take this outside, because it's smaller than a constant epsilon over b minus a, and the only think about the sum of delta xk, then this part will equal to b minus a, right? Then b minus a cancels. This is epsilon, right? Or because originally I was trying to say that, well, like lambda over b minus a times, well, because delta xk is smaller than delta, then I was thinking that maybe n times delta n times delta. But then you will decide, you will also think about n times delta, what n times delta is gonna be like, right? Well, and that took a step back from what we want to prove. So just grab it. And well, finally we have proved that if a function is continuous on AB, then it is also integrable on AB. And well, this is what I want to show in this video, and in next video we will have some more interesting properties and theorems about integrability. So hope you enjoy it, and see you in next one.